Greetings. In this one, we'll talk about something called a discrete and an indiscrete topology. So, a topological space, as we've talked about before, there's some x, set x, and on that set we have topology, tau, usually with these names. Now, if you're talking about discrete and indiscrete topologies, those are probably the two basic ones one gets confronted with very early on as studying through topology, because they're very basic and they're basically the simplest cases one might consider when thinking of a topology. We know that a topology requires empty set, the entire set X itself, because topology is the collection of subsets of X that satisfy some conditions. Now I'm gonna say those conditions. There must be empty set, there must be the entire set X, and then there must be such other subsets such that if you take any finite intersection of them, that result will again be one of them. And if we take any infinite or whatever union of them, that will also belong and also be one of the subsets in the collection of subsets called tau, in that topology, which is the collection of subsets of X that satisfy these three conditions. Now, to satisfy these conditions, we could think about a very trivial example, and namely, that's called indiscrete topology. An indiscrete topology what it means is we can think of the very simplest example, and that is namely that a topology really consists of just the explicitly stated mandatory subsets. That means the empty set and then the set X itself. Well, does that work out? Well, it does, because first of all, we satisfy the first requirement straight away. Second of all, the second requirement is satisfied as well, because any union, well, union will be X. Intersection will be X. Intersection here will be actually nothing. Then union will be X. And there's no other union we can take because there's just these two elements, or these two subsets inside this collection in this topology. That means that this actually does satisfy the axioms, the requirements for a topology on set X, and it is a valid topology. So it's called indiscrete or also trivial topology. And then there's another kind which follows the similar philosophy, but from the other side. It actually doesn't do the minimalistic view, but actually this does the other side, the maximalistic view. That means it takes into account all different possible subsets. That means that this topology, it contains first of all the empty set and the entire set itself, the underlying set X itself, and then it also continues with all sets A such that A is a subset of X. What this means is basically that this is kind of redundant because these are also subsets of X, right? But what we are saying is mainly this part, that all different possible subsets of X we're taking into account. And this topology, of course, it will satisfy the rules. If we take intersection of any finite number of subsets, well, we're again going to get some subset. And as we have all subsets taken into account with a discrete topology, it's going to work out. It's going to again be a member of the topology. A second thing is union of any number of subsets, well, again will be a subset of X. And we have all subsets inside that list. Therefore, it will also work out. So what we look at here is we can have topologies, first of all, in the minimalistic trivial view, counting with just the empty set and the entire set itself. And another case could be that we actually have this satisfied, of course, but we actually look at the whole picture and we take into account all possible subsets of X. Thereby, we really make sure that all will be there and all three requirements are met.